Hello, this is Mr. Allen, and today we are going to continue our discussion of Chapter 3. We are going to be looking at Section 3.5, which is on curve sketching. Our objective here is to analyze and sketch graphs of a function. I will say that I think that this is something in my years teaching calculus that I kind of took for granted, but it's something that I think is very important. Maybe one of the more important applications of calculus is the fact that now that you know all of these things about the derivative, this should help give you really good insights into what curves look like of functions that you don't even know. And I would just remind you that there are several curves that you should already be familiar with, things like the graph of y equals x, y equals sine x, y equals 1 over x. I guess I could write some of these down. So, y equals x, that's the identity function. Y equals 1 over x. Y equals sine x. You should be familiar with these, and there's 8 of them that I told you at the beginning of the year you needed to be comfortable with. Anyways, those are the basic functions. But now that we have calculus in our belt, we can analyze curves that we aren't so familiar with. So when you are sketching the graph of a function, either by hand or with a graphing calculator, remember you typically can't show the entire graph. So that's typically, why we put the little arrows at the end of the graph. The decision as to which part of the graph you choose to show is often crucial. In fact, the quiz you took, or I'm sorry, the test you took on Chapter 2, there was a question that I asked at the very end about sketching the curve of a function, and I gave you the domain, and I'm predicting that I'm making this video in late October, and we're now well into November, December. Some of you probably missed some points on that graph, which should have been easy points because you didn't show all the curve. So for example, let's say we're looking at this function here, which is f of x equals x cubed minus 25x squared plus 74x minus 20. If you set your window from -2 to 5 and -10 to 40, you'll get this shape here. In fact, you might think that that's just a parabola. An untrained student might think that from Algebra 1. However, when we change our window from x going from -10 to 30 and the y min from -1200 to 200, you can clearly see that this is a cubic, which should have been apparent all along. By seeing both views, it's clear that the second viewing window gives you a more complete representation of the graph. But would a third viewing window reveal other interesting portions of the graph? So in other words, what if we extended this out further? Would it give us more information, important information about this graph? To answer this, we need calculus to interpret the first and second derivatives. Here are some of the guidelines for determining good viewing windows for graphing functions. Number 1, determine the domain and the range of the function. So this goes all the way back to Algebra 1 and Algebra 2 and pre-calc. 2, determine intercepts, asymptotes, and symmetries. Again, this goes back to Algebra 1, Algebra 2. But now we've got this third component. Locate x values where f prime and f double prime are either 0 or d and e. Use those results to determine the relative min, max, and also points of inflection. Now, guys, I'm going to do an example here that I'm pretty much going to just pop up all the information you would want to. If you actually had to do this, it's a pretty long process. So here's a function, and what we're going to do is we want to analyze and sketch. Analyze means we want to get all the important details from this graph that we can, this function's graph. So first thing we could do is we could find the first derivative. We would use the quotient rule for that. We could also find the second derivative, which, by the way, finding the second, getting the first and then to the second derivative definitely requires some work, but I've got those done for you right here. Now the x-intercepts, remember, to calculate x-intercepts, you let y equals 0 and then you solve. And hopefully you realize the only time that that's going to be 0 is when x is plus or minus 3. To find the y-intercepts, you're going to let x equal 0. So if you plug 0 in for x, you'll figure out that it turns out that it's 0, 9 over 2, or 4.5. Vertical asymptotes. How do we find vertical asymptotes? Well, I hope you remember that the way we find vertical asymptotes is we take the limit of the function to plus or minus infinity. That is the, oops, I'm sorry, that's horizontal asymptotes. Sorry, horizontal asymptotes is when you take the limit of the function to plus or minus infinity. Vertical asymptotes, let me get that correct, I apologize. This is when the limit of the function as x goes to some value, I'll call it c, is equal to plus or minus infinity. That's how we define. This is going way back to chapter 1 in our book. So let's see here, continuing on, critical numbers, that's where you set the first derivative equal to 0 or d and e. Again, this is a review from chapter 3. Possible points of inflection. Well, when you look at the second derivative, you'll see that there are actually no changes in sign of the second derivative. Domain in this particular example is all real numbers not equal to plus or minus 2. The range, I'm sorry, the symmetry, it has a symmetry with respect to the y-axis. In other words, if you plug in negative x into the function, you will get f of x. That's what it means. This is how you find, and this is also review from things you've done in the past. So to find a symmetry with respect to the y-axis, if you plug negative x into the function, you will get f of x. If I had plugged negative x into the function and I got negative f of x, then that would tell us that we have an x-axis symmetry. And so here are our test intervals, and notice that these test intervals are coming from our domain here. So now I've got a table here all set up with all of this stuff. So looking at the second derivative, we see that it is negative on the interval negative infinity to negative 2. That makes it concave down. The first derivative is also negative there. That makes it decreasing. Now notice I didn't put anything here for f of x because that's not going to help me right now. I don't necessarily need to know what's going on. What's important for me to know is that the function is decreasing, and it's decreasing on this entire interval, and it's concave down. At x equals negative 2, I should do this in red, it's undefined because you're dividing by 0. So this is going to be a vertical asymptote. In other words, on one side of this point, it's going to be going to, the limit's going to go to negative infinity. On the other side, it's going to go to positive infinity. Now our next interval, which is negative 2 to 0, we can see that it's still decreasing, but now it's concave up. So it was going like this, and now it's still decreasing, but it's concave up, so it's got to be going something like this. X equals 0, that's our relative min. That's our relative min. And the reason that we know it's the relative min is because, I'll do it purple, the first derivative changed sign from negative to positive. Notice that the second derivative is positive there, so that tells us that it is also concave up there. Anyways, you can continue going through this, and after you've looked at all this data and this information and use the fact that it has a symmetry with respect to the y-axis, and use the fact that you know that it's increasing here, and you know that it's decreasing there, and you know that it's concave up here and it's concave down there, you know that it has x-intercepts and all of those things. Now we can use all that information. Now notice that it had a horizontal asymptote, y equals 2. So that means the limit of this function as we took x going to infinity was equal to 2. Notice that, and I'll do, yeah, it's in red. Notice that it was concave down and decreasing here. Notice that it was concave up. Concave up and decreasing there, just like we said in the table. But then when we get onto the other side of the x-axis, it was concave up and now increasing over here. And then here it was concave down and increasing. So all of the information in the graph corresponds to the information we found in this table. Now, again, I'm just going to tell you, this takes time. So the assignment I give you will not be very many questions because doing all of this takes a lot of time. But you can really dig into what the graph looks like without having to use your graphing calculator. And then once you do all of that, then you grab your graphing calculator and see that you verify, oh yeah, it was increasing there. And oh, it was concave down there. And yeah, there was a point of inflection. So you try to do all this stuff without the technology, and then you use the technology. Okay, there's one more thing I want to talk about on this particular video, and then we'll call it a day. And this is actually supposed to be a topic that's taught in Algebra 2, but I know that's been a couple of years ago, and I'm not, I don't know for sure that your teacher all taught this or how much they emphasized it. But we've talked about vertical asymptotes and horizontal asymptotes. I want to mention a slant asymptote. In fact, let me just show you a picture of a slant asymptote. So this is our function here. This is a slant asymptote, and this particular slant asymptote has the equation y equals x. So I just want to show you how to find a slant asymptote without being told what it is. We already know how to find the horizontal asymptotes and vertical asymptotes through calculus. Now I want to show you how to do it. So here's the same function, and I want to find the slant asymptote. And so here's what you do, and it's written right here. You're going to use long division, okay? In other words, you're going to do x squared minus 2x plus 4. You're going to divide this by the denominator. And so let's just go ahead and divide. So x times what gives you x squared? Well, that just be x. So x times x is x squared. X times -2 is -2x. And then we subtract. So when we subtract here, that's going to be 0. That's going to be 0. So we're left with 4. So x does not go into 4. So this is what we call our remainder. So that means that this function, and in fact, I'm going to rewrite it, f of x can now be rewritten as x plus, and now I'm going to put the remainder over the divisor. I would just challenge you if you don't believe that that's true. I'm telling you that this expression is equivalent to this expression here. So how do we find the equation of the slant asymptote? It's simply this right here. You ignore the remainder part. It's just y equals x. And I should probably make sure that I don't jump over this too quickly. These slant asymptotes are only going to happen with rational functions that have no common factors and whose denominator is 1 degree or greater. Okay. In other words, what I'm saying is this. So this is a rational function. It's a quotient of polynomial functions, and you'll notice that this is x squared and this was x. So we have a degree difference of 1, and so that's why we're going to get a slant asymptote. In other words, so when you go to sketch this, and again, this would be a problem that would probably be on a no calculator part of the test. You can sketch this line here very easily. You know there's a vertical asymptote here. And so then when you sketch this, you'll find that there's a relative min here in the middle. It allows you to draw a really nice graph when you have those slant asymptotes. So anyways, so we're going to stop it there. Thanks for your attention. And this is section 3.5, curve sketching.